Okay, let's continue our discussion about steady state error. Remember, what we're trying to do is look at the steady state error, what happens to the system after the transients are gone, and we're trying to maintain a certain level in the system. And we call this steady state error. It's a parameter that we have to be mindful of in many of our design cases related to control systems. We've been working our way through this and figuring out how this is going to work. And my tablet locked up again. And we talked about it initially just kind of in a hand-waving way, recognizing the fact that if we have some little error between where we are and where we want to be, if we integrate that error over a time, then our signal would get large enough to push the error to zero. And so, and that is an integral controller on a standard control system. And so that's what we've been exploring in here is how that actually works. We went through the theory of that. We developed this equation that defined the error in terms of our block diagram elements, and then we subjected that to the final value theorem to find out what that error was at infinity. And that general equation will work in any case. Okay, any case. If you know what the input is, you know what the open loop transfer function is, you can calculate the steady state error with that equation always. Okay, but it gets a little cumbersome at times, and it's not exactly where we want to go, and it doesn't lend itself to a lot of understanding. And so we pushed on and we developed that equation. We refined that equation down to three specific conditions: a step input, ramp input, and parabola input, and developed equations for that. From that, we then applied it to some various transfer functions. These transfer functions had no free integrator, one free integrator, and two free integrators. And we looked through and saw what each of these did as a response to the step input, ramp input, and parabolic input. And we found some interesting things in here. We found that there was a cluster of them that had zero steady state error. There was a cluster that had infinite steady state error, and there was a cluster also that had a constant steady state error. And so using this idea is where we move forward today and see if we can develop a little bit easier way of thinking about this. And this gets into some new terminology. It's not hard. It's system type, and it's a fancy name for the number of free integrators. That's all it is. The system type is the number of free integrators. How many S's do you have in your denominator of your open loop transfer function? That is the system type. And if we take that and apply it to this scenario or similar scenarios, we can come up with a nice little table in here that you see right here. And what it is a relationship between the step, ramp, and parabola, and the type 0, type 1, type 2. Type 0 being no free integrators, type 1 being one free integrator, type 2 being two free integrators. And we see that we have a zero steady state error, and we have infinite steady state error, and then we have the case where we have a constant steady state error through here. Okay. Now, in reality, this is very informative, and it can help us intuitively to figure out what it is that we need to know and where we need to go with this. If you're looking at a system and you know from the specifications that you need, it's going to be a constant input, like an oven, okay? Constant input, and you want a zero steady state error. You know that you have to have a type 1 system. You have to have at least one free integrator in your open loop transfer function in order to get a type 1 system, okay? If you come up with a system that has a ramp input, again, if you had an oven, a commercial oven that had some sort of ramp up, ramp down, and then a steady state in between, and you wanted zero steady state error on that, you would know that you would have to have two free integrators in the open loop transfer function in order to make that a reality. Now, there is the case where there may be some error that is acceptable, in which case you would need to go in and calculate the error for the non-zero constants. Because remember, adding free integrators tends to push you towards instability. So while we use them cautiously and in limited amount because of their instability on the system. So we don't want to push it farther. In this case, where that I was just talking about with the oven, where we ramp up steady state and then ramp down, it may be tolerable for to have a steady state error, constant error ramping up, and then be constant across the step input, and then have a constant error on the way down. You're delayed in time just a bit. Maybe that doesn't matter. Maybe it does, depending on your application. But that would be something that, as the designer, the engineer on the project, you would determine, and in which case you could do a type 1 system on this and have an adequate system for the application. Now, this next bit in here is just a little more refining of that. We have these in this particular graph. We have some a KP, which is just actually the denominator or portion of the denominator for each of these cases: the step, the ramp, and the parabolic Kp, Kv, Ka. Now, these are not gains. These are just constants used in calculating the constant value associated with this. Here's the same table again. We see the zeros here. We see the infinities here. And we see the constants. Now, in this particular case, and why I included it in this, is because the constants are defined for you here, here, and here. So you can, by calculating the Kp or the Kv or the Ka, depending on your interest, then you can calculate the value of the error for each of these conditions, which have a constant error associated with them. And for the step, ramp, parabola, for the type 0, type 1, and type 2. And so, honestly, a bunch of these cases come down to this simple table. Actually, it comes down to this simple table. You got 6 out of 9 chances that it's either, or 3 out of 9 that it's 0, 3 out of 9 that it's infinity, and then you have to you may have to calculate the other 3 cases. So it's very common for me to ask on an exam, give you a really, really nasty system, and ask you what the steady state error is, and it's typically in one of the cases either 0 or infinity. You say, oh, well, it's got 2 free integrators, it's a step input, it's 0. It's got no free integrators, it's parabolic input, it's infinity. And typically there's no calculation involved. You just have to recognize those cases. So watch out for that, because that's a little hint on my testing practices there. But anyway, these tables are very, very helpful, and you should glean some intuitive kind of knowledge from them also. If you need to lower the steady state error, you're probably going to be adding some integrators, some free integrators in there, an integrator term. And so that's it. And I'll probably go ahead and do some examples here in the next couple lectures.